Thursday that when we were deriving our radian measures for our various angles, we started with the degrees, worked our way to the radians. Now, the way we did it for quadrants 2, 3, and 4 were different than this. We certainly could have taken this approach, but we instead kind of used some of the things that we noticed, some of those patterns that we noticed in quadrant 2 being slightly less than a half rotation, slightly more than a half rotation, or less than a full rotation, in order to kind of fully derive what we were looking at there. But for quadrant 1, I did something in particular right at the start that allowed us to take this 30 degrees and say, well, I know that it must correspond with a radian measure of pi over 6. What was it that led me to that conclusion? Why does 30 degrees have to go with pi over 6?
30 degrees 6 times into 360.
Okay, so 30 degrees, how many times is 360?
Right now,
12 times would be 360. So in particular, if I have 30 degrees out of a total possible 360 degrees, how much of my circle have I rotated around? What fraction of my circle? 1, not 6th, but 12th of my circle. And then thinking about what I have to do to go from that into radians, what does it mean to travel a 12th of the way around my circle in terms of radians? Well, what is going all the way around my circle in terms of radians? 2 pi, that's like the equivalent of the 360 degrees. And so a 12th of 2 pi gives us 2 pi over 12, okay, but we're really going to refer to this instead as pi over 6. Okay, so this strategy that we have here, taking our angle measure that we're given, in this case, we started with degrees, saying what fraction of our circle does this represent? So think of 1/12 here as the fraction of, you could also think of this, and this is going to be very, very nice as an intuition for what we do on Wednesday. You think of this as like what fraction of a full rotation do we have? Or you could think of how far have we gone around the circle. So fraction of a full rotation or full circle, however you want to phrase it. And what are we doing with that fraction? Well, we are applying a new whole. What do we actually want? What does it mean to go all the way around the circle in terms of this new value that I care about? In this starting case, it's going to be radians, but we'll see it applies to like circumference and area and degrees and all that as well. This is a very, very pervasive logic that we can use. What part of our circle, how much of our circle do I go around? If I go around that much of my circle, then I must cover that part of my whatever whole thing that I'm looking at, that part of my area, that part of my circumference, that part of my total possible radius. Now we could also do the exact same thing in the other direction. We didn't, but we certainly could. And this ultimately is a little bit of a crutch, but we could do it. If I, for instance, started with pi over 6 and we're pretending that this isn't one of our significant angles that we just kind of know, and it's certainly not written up here, that'd be ridiculous. If I want to figure out by this kind of exact same methodology, or pi over, we already did pi over 6, let's do pi over 3. If I wanted to figure out by the same methodology, how would I figure out what fraction of my circle pi over 3 represents?
Divided by 2 pi.
Divided by 2 pi. Now this is a little bit awkward, just in terms of kind of how this looks. But you could think of this as like a third divided by 2. When you divide by 2 pi, you could also think of multiplying by 1 over 2 pi, multiplying into the denominator either way. And when we do that, what fraction of our circle is this? You could also enter it into your calculator if you're deliberate and clever about it, but we'll take a look at that. What fraction of our circle do we have here?
1 over 9.
a 6, so 2 times 3 in this case, would give us a 1/6 of our full kind of rotation here. That 1/6 is really cool and all. What do I need to do in order to convert that to degrees? What would it mean to go all the way around my circle in terms of degrees? It would be a total of 360 if I'm going a 1/6 of the way around my circle. 1/6 times this 360 is going to give me my degree measure here, in this case, 60 degrees. Okay, how could we take this and generalize it? It's not too difficult to do. For instance, we could say, if I wanted to have theta in terms of degrees, well, this is going to really be theta in terms of radians. I'm using the subscript r just to denote that this theta is in radians, divided by the total number of possible radians, in this case 2 pi, to figure out the fraction of my circle and multiply it by the new whole here, in this case 360 degrees. Alternatively, if we wanted to find our theta in terms of radians, we could take the theta in terms of degrees, figure out what fraction of our circle does that represent, multiply it by 2 pi. Now, if you've worked with radians and degrees before, I'd probably bet that you haven't seen this conversion vector, that what you instead have been given is that you're looking at like multiplying by 180 and dividing by pi, or multiplying by pi and dividing by 180. And you can mess around with this and you'll see that it simplifies to saying the exact same thing. I like this though, just because it carries with it this really cool intuition of first identifying the fraction of the circle. In both parts, and we'll see that this is a cool idea that we can use for a lot of other things, and then adding in or multiplying in really a new whole value. What does it mean to go all the way around the circle in this slightly different context? So if going all the way around the circle before was going 2 radians, now it's 360 degrees. All right, questions with the logic that we're working with here? Yeah, a little subscript r, just to denote, because like we have a degrees symbol to say I'm in degrees. We don't really have anything to indicate that we're in radians, so I use this little subscript r to just say, hey, the angle measure is in radians. Yeah. All right. Let us then take a look at, we're going to look at example 1 and 2 kind of in tandem here. Both of them are asking us to convert between radians and degrees in some capacity. So for example 1, we are given degrees and being asked to convert to radians. Example 2, vice versa, going to be doing the opposite here. So looking at 1A, we are given 15 degrees, trying to figure this out in terms of radians. What do I need to do first? What do I use this 15 degrees for primarily? Divide by 360. What fraction of our circle does a 15-degree rotation represent? Yeah, this is going to be 1/24th. You could use your calculator for that. You could also note that it is half of our 30-degree rotation, which we said is 1/12th. So it's going to be 1/24th. Very good. And then what am I doing with my fraction here? So this is like my fraction of the circle. And what do I do with this? Multiply it by 2 pi here. What is the new whole? And in this case, we get 2 pi over 24, but we'll simplify that down. That's going to be pi over 12. All right. Questions with 1A? We can do the exact same thing for, well, 1B and C, but I'll let you guys do that here in a second. We're going to do the exact same logic for 2A. So on the next page, we're given pi over 24 as our radian measure. We are trying to figure out what does this look like in terms of our circle. What is going on here? And so what do I do first if I want to convert this into degrees? What do I first find? What fraction of the circle this is. And so we are going to divide by 2 pi. So notice before a full circle was a 360-degree rotation. Now it is a 2 pi rotation. Plug it into your calculator or multiply into the denominator and cancel some pi's. Either way, I get that this is 1/48th of a full rotation, full circle. And what do I need to do to convert 1/48th of the way around my circle into degrees? Multiply by 360 degrees. And this works out to be like 7.5 degrees, notably half of what we found from example 1, but we certainly didn't need that inference. Certainly could have it.
That's 7.5, right?
Yeah, 7.5. 7.5 degrees. All right. Questions with example 1 and 2? Basically, yeah, when you're dividing a fraction by a whole number, you multiply that whole number. Just not a fraction. 2 pi is obviously not a whole number. But you multiply it into the denominator. Yeah. All right. We're going to take 5-10 minutes. Take a stab at the rest of example 1, the rest of example 2. A couple of things that I want to note. First and foremost is that when we are working with trig, you will notice we've got a lot of pi's, we've got a lot of square roots. Pretty much all of our answers are going to be irrational, which means that decimal approximations are going to not be good enough. Right? Oftentimes, I will ask you to give me an exact answer, which will require us to be able to work through this essentially without a calculator. Right? So that can be tricky, but ultimately, I think this methodology lends itself pretty well to it. If you wanted to, You can always, to figure out what's going on with your calculator, you've got a whole string of stuff being multiplied together. You can always multiply the stuff that doesn't have pi and then just put pi in the numerator or denominator wherever it belongs. That would certainly work. I would say the exception of that I would give you guys is for 2b. You can use a decimal approximation for that one, but for 1b and c and 2c, exact answers for those values. I mean, you can just leave it like that as well.
Okay,
And that would be fine. But like, how would you simplify it? So the 2 here will cancel with the 2 down here. Still have like 173 pi over 36.
oh, because this is multiplied.
Yeah, when you have like fraction times not a fraction, think of it as like 2 pi over 1. That's pi. Yeah. You could plug that into that one. That one actually comes out to be a really nice decimal. So you have that into your calculator. Yeah, that's exact. 0.35 times 2 pi. Yeah. Certainly works. I just don't want you to then take that 0.7 pi, plug it in, and give me that that's like 2.547, blah, 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 because that's not very useful. 0.7 pi actually is like a fairly useful thing. Okay, so it's going to be the exact same idea. Stuff's just not going to cancel as nicely. So this looks a lot neater than like pi over 24, pi over 24 actually. This is going to be the gross number. So this is the radian measure. What do I do to figure out how much of my circle that's going to be? Divide by 2 pi. That gives you your fraction. You can leave it like that, like 3 over 2 pi is a valid way to write that fraction. And then like multiply by 360, and that's perfect. You're done there. But you could also convert that. It's like 0.477, blah, 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 and then multiply that by 360, and that will give you the values. Yeah, so decimal approximation there is fine because numbers are just kind of nasty, and it's not super often that you'll end up with pi. No. Yeah, I would use a better calculator. But also, if you wanted to, you could just take that, and then what you would do is like a fraction of the circle. So you would need to multiply it by 360, so you could just do like 3 times 360, it would give you like 1080. So like 1080 over 2 pi with total, that would be like a more precise number. What you get was. It'll simplify a little bit, but it's going to be still pretty nasty. When you multiply by the 2 pi here, it's just into the numerator, so it'd be 14 pi over 20, and then simplify to 7 pi over 2. Okay, so looking at B here, where do we start with our 126? So divide by 3 to figure out what fraction that represents, how much the way around this circle that is. This one will actually work out. And then what would we do with that once we have the fraction?
Because you can do different, right? like that fraction. As opposed to just.
Quick thing that I want to note. If you're gonna write it like that, I would just leave it as. Quick thing to note, in your calculators, if you're using the fraction operator, you'll be totally fine. This won't be an issue for you. If you're using the fraction, if you're substituting in the division for the fraction, for instance, if you try to write 3 divided by 2 pi like this into your calculator, calculator does not read that as 3 divided by 2 pi. It reads it as 3 divided by 2 times pi. And so what you were going for was this. And what it sees it as is this. So it displaces your pi from the denominator and puts it into the numerator. A couple of easy way to fix that. I would say the easiest is just put parentheses around 2 pi and run from there, and that'll fix the issue. But also, if you were using the fraction operator, then you would get the 3 over 2 pi anyway. So again. Question? Perfect. You can do that, yeah. Well, no, because you're multiplying by 360, so you're multiplying the numerator. So it'd be like 19 over 8 is divided by 2 pi. 2 multiplies that, and pi is canceled. 19 times 360 divided by 8. All right. Let us take a look here. Looking at B, where do I lead off? What do I do with this 126? Divide by 360. Find that piece of the circle. What fraction of the circle does this represent? What fraction of the circle does this represent? 7/20ths or 0.35. Either way, in this case, actually ends up being totally fine. Just making sure that we are being precise at the end. And what do I do with this fraction? Multiply it by 2 pi. You can totally leave it like this. First of all, that's totally fine. You could also write this as 14 pi over 20. I'm going to write this as the simplified 7 pi over 10. For 865, what am I doing? Exact same thing, dividing by 360. This works itself out to be something nasty. It's like 173 over 72. And then we multiply by 2 pi. 2 is going to cancel here. This is going to become 173 pi over 36. A little nasty, but not too horrible. And you totally could have written that as 346 pi over 72, and that would have been fine as well. Or you could circle this, and that would also be totally correct, totally fine. All right, for B, I think B threw maybe a couple of people off just because no pi. But our methodology is going to be exactly the same. If we are given radians, how do I take this and convert it into my piece of the circle? Divide by 2 pi. Not a whole lot that I can really do with 3 over 2 pi. You can plug it into your calculator, get a decimal. We could also just leave it like this. What are we going to do with this? Multiply by 360. In this case, degrees. 360 times 3, you could do 1080 over 2 pi, or you could do 540 over pi degrees. Which is a little bit silly looking, but also radian measures of whole numbers are just a little bit weird, and they're not going to work out to be very clean. 171.89-ish degrees. All right, and then for 19 pi over 4. Exact same idea, divide by 2 pi. This works itself out to be like 2 3/8 of the way around the circle. And then what are we doing with this? 2 3/8 would be 9, I guess just 19 over 8. Makes sense. I multiply this by 360, and correct me if I'm wrong, but I think 855.
So the numerator doesn't really change a lot, does it? It mostly affects the denominator.
Yeah, because we're dividing. Well, it would depend on what we end up multiplying by, but for the most part, yeah. Notice that we do have some cancellation going on here. So when there's cancellation, that 2 pi isn't really going to affect much. But if we didn't have cancellation, like we could have totally written this as 14 pi over 20 as well, and that would be fine. But that's just because we're multiplying by 2.
Wait, cancellation?
Yeah, so like 7 over 20 times 2 pi, I cancel the 2 from here and from here to simplify it to 7 pi over 10. But you also can write it as 14 pi over 20. 7 times 2 pi is 14 pi divided by 20 over 20.
I thought it was just because it was dividing.
Well, here we're dividing by 360 and then multiplying by 2 pi. Over here we're doing the opposite.
What if there isn't a 2?
If there isn't,
You said we were canceling out 2 from 2. What if there isn't?
what if there just isn't anything that cancels? Then you would just multiply this into the numerator and you go like that. Which we kind of see, well, I guess we don't. We have a little bit of cancellation everywhere, huh? But yeah, like if we needed to write this, like if this was a 73, we could write this as 346 pi or 73. You just multiply into the numerator. Think of it as like 2 pi over 1, multiply the numerators, multiply the denominators. The over 1 isn't going to change the denominator much. But we do see kind of this denominator being created by the dividing by 360. Other questions? All right. Fantastic. Let us then, I want to highlight something really quickly before we move on about 2C in particular, but then I'm going to make the same point about 1C as well. 19 pi over 4 kind of implies that this is going to be like one of our pi reference angles. Should behave fairly similarly to what we see here. But do we have 19 pi over 4 on our unit circle? Yeah. So why then do we have this pi over 4, this 19 pi over 4, pi over 4 reference angle that doesn't exist on the unit circle? It's not a main point on the unit circle because it is not because it's irrational. It's bigger than 2 pi, bigger than a full rotation. 19 pi over 4, what would a full rotation be for radians? That's our 2 pi. What's maybe a nice way to compare it to 19 pi over 4 that we can make it really clear that 19 pi over 4 is bigger? Say maybe 2 pi is like 8 pi over 4. And so as it stands, ultimately, we're not able to do much with the 19 pi over 4. Not that we're really being asked to do much with it. We're just being asked to convert it to degrees. But in the future, we're going to be asked to find the corresponding x and y values that are associated with this angle. And as 19 pi over 4, it's very difficult to tell where it's going to end up. We know it's going to be in one of 4 locations, but which one of those 4 is maybe going to be a little bit difficult to parse. In particular, because I am over-rotated. I am rotating all the way around my circle, rotating all the way around my circle some number of times before I finally come to my final resting place, and asking you guys to memorize the infinite number of ways that I can rotate around my circle in different ways would be not just unreasonable, but frankly impossible. We could rotate backwards around our circle, we could rotate 500 billion times and then come to a stop. Too many ways to do it. And so we need a mechanism by which we can unrotate and get back to the useful information that we have. What could I do to unrotate from 19 pi over 4? Or maybe easier than that, my 865 is also over-rotated, bigger than 360. What could I do to unrotate those extra kind of loops around my circle that I've done with my 865? Yeah, subtract 360 until what?
Until you get less than 360.
Until we get less than 360. Very good. So we could take 865 and we could subtract 360. This gives me 505, which is better, but still not quite there. So subtracting another 360, I get that this is very similar to 145 degrees. What about it is actually similar? So in some way, these 3 angles share something that is important, that is relevant, that is making me want to unwind them. But are they the same angle? Is 865 the same as 145? No. There's information in 865 that sets it apart from 145. In particular, it's that it's rotated twice all the way around the circle before rotating an additional 145 degrees to come to its final resting location. Within that explanation, though, there's a little bit of a hint. What do they share? They share the same resting location, right? 145, 505, 865. What's different is the actual rotation itself, the direction or the number of times we're rotating around the circle. What they share, though, the important information that ultimately we're going to want to tease apart is what points do they correspond to on our circle? What is the terminal side? What is the final resting location? Angles like these are called coterminal angles. And really, it's in the name. They are angles that share kind of a final stopping point, or a terminal side, which is why coterminal angles, toe being with, terminal being that final side. So angles that share a stopping point is how I'm going to describe it. Casually there. And so rather than, again, memorizing the infinite number of different ways that I can write 30 degrees, I could write it as 390, I could write it as 750, blah, 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 so on and so forth. Rather than doing that, we are instead going to just learn 30 degrees. And then whenever we have an angle that is really, really big or very, very negative, we're just going to adjust. We're going to either subtract off full rotations or add on full rotations until we see a number that we're happy with, until we see a number between 0 and 360. Now we could do the exact same thing with pi over 4. In fact, we already know pi over 4 is 855. We could subtract 360 from it over and over and over again, and so on and so forth. But if I just was given 19 pi over 4, I wanted to adjust it in radians, rather than subtracting 360 from it over and over again, what could I subtract from my 19 pi over 4? 2 pi. A better way to subtract 2 pi, subtracting this 8 pi over 4 over and over and over again until it would turn me negative and I can't do it anymore. So 19 pi over, well, not can't, but it would be fruitless to, minus 8 pi over 4, we get 11 pi over 4. And 11 pi over 4, is that going to be more or less than a full rotation? Still more. Our full rotation is 8 pi. 11 pi is definitely more than that. So subtracting away that 8 pi over 4, and I get 3 pi over 4. And so from this we learn, oh, hey, this is a Q2 angle. And it is kind of similar in many ways to pi over 4, but very similar to our 3 pi over 4. The final point that we would see is that point that corresponds with 3 pi over 4. Is 19 pi over 4 the same as 3 pi over 4? No. It just shares a final resting location, which ultimately is kind of the information that we actually want from these angles. So in many ways they are similar, but they are not the same angle. 3 and 19 are not the same. Okay, we'll see this come up a little bit later. I just wanted you to really be aware of it, of this idea that technically there are an infinite number of ways I can write any of these angles, and we'll just adjust them to fit the ones that suit us best. And we'll deal with those more as they kind of come up, but just so that you are aware that this is a potential issue that we will sometimes have to deal with. Is equal to. And then 11 pi over 4 minus 8 pi over 4. Okay. Right. Questions with examples 1 and 2? What's the full rotation in terms of radians? In terms of radians? 2 pi. And what would that be if I want to match it with my denominator 4? 8 pi over 4. It would be a full rotation in terms of pi over 4. Okay. Yeah. I could have done in terms of pi over 6 as well, 12 pi over 6 or 6 pi over 3, various things like that. The relevant one here, though, pi over 4. All right. How we feeling? Pretty okay? Questions? Okay, we're going to take this exact same idea, the idea of figuring out what piece of our circle are we looking at, what fraction of our circle have we been told that we are given. And now, rather than looking at converting from angle to angle, we're going to convert from angle to other things or other things to angles. There are other facets of our circle that we care about beyond just what is the theta that we are looking at. All right. We are going to focus on 2 of those facets today. First one is going to be arc length, which I could define very, very uselessly as the length of the arc. I'm going to define it hopefully in a slightly more useful way. The arc length is going to be a piece of our circumference. Now hold on a second. What makes this different than radians? Well, nothing on the unit circle specifically. So recall, radians were the distance that we walk on our unit circle around the circumference. The reason why 2 pi as a full rotation is the circumference of our unit circle is 2 pi. But arc length is a little bit more generic. We can talk about arc length with circles that aren't just the unit circle. But there is a very, very clear draw between the radian measure, which would be like the arc length along the unit circle, and just a generic arc length. And we'll look at how that actually metastasizes in the formula itself. But really, just kind of keeping this underlying notion here of we are now walking along the circumference of a circle, no longer with just a specified radius 1. Radius can now be whatever we want it to be. If we are looking at the arc length as a piece of our circumference, and I give you that circumference, or that piece, let's say, is created by a 90-degree angle. How could I take that 90 degrees and convert it into that distance that I traveled, that piece of the circumference? Yeah, so find out how much of our circle does 90 degrees represent. So dividing by 360, 90 degrees is equivalent to 1/4 of our full circle. And then what would I do with this 1/4? How would I figure out the arc length? Well, if I traveled 1/4 of the way around my circle, then I have traveled 1/4 of the way around my circumference. What is the circumference of a circle? 2 pi r. Right, obviously, we're not always going to be given 90 degrees, but we can take this idea, we can make it generic very, very easily. Arc length, if I am given, in this case, S equal 2, if I am given a theta in terms of degrees, we think theta degrees out of 360 degrees. Again, what fraction of our circle are we walking around? Multiplying this by our 2 pi r. And if I'm given a theta in radians, how do I figure out the fraction? Take it and divide by 2 pi. And then what would I multiply by to convert into that edge? 2 pi r. Still looking at piece of our circumference. Again, exact same thing that we just did. We still are finding the fraction of our circle. And we are now multiplying it by what it means to go all the way around the circle, just in a new context. Right? Before, we were doing degrees, where 360 degrees would be going all the way around our circle, or radians, where 2 pi would be going all the way around our circle. Now we're doing the circumference, where the full circumference is going all the way around our circle, that 2 pi. What could I do with my formula in terms of radians? What's going to actually happen here when I do out this multiplication? I'm dividing out by 2 pi, and then what am I immediately doing next? Multiplying by 2 pi, or what's going to happen with those 2 pi's? They cancel. You'll often see arc length written in the form of theta in terms of radians times the radius. If you've done arc length before, this is probably how you've seen it. There's nothing wrong with this. This is totally fine. The reason why I am going to default to this One is because I really like the logic. I just think it's kind of nice and consistent with what we've been doing up until this point. So I just enjoy how it kind of melds together a little bit more seamlessly. But also I think people can kind of get confused. They remember theta times r, but then they don't remember that it needs to be the theta in radians times r. And so they end up like multiplying the radius by like 274 degrees, which does not get you the arc length. It gets you nothing. A quantity that is completely useless. And so just to kind of like keep ourselves grounded, I like starting out by figuring out this fraction and then just multiplying by the new whole. I don't think that's particularly more difficult than memorizing that it's theta sub r times r. Of course, you are more than welcome to approach this however you like. If you like to default to theta sub r times r and you want to start every problem by first figuring out theta in radians and then multiplying it by r, you can totally do that. That's totally fine. I just think that the logical consistency of figuring out the fraction, multiplying it by the new whole is a little bit easier. And it cuts back on the amount of memorization that we have to do, which I'm always a big fan of. If arc length is a piece of our circumference, sector area is going to be a piece of our area. So thinking we've got our like start point here, we rotate around all the way around. Certainly we could rotate and fill out a full circle. Realistically, we're probably going to stop somewhere along the way. The arc length is going to be, again, the length of the arc that we trace out, a piece of this full circumference. And the sector area is the corresponding area that goes along with it, which again is just a fraction of our area. If I travel halfway around my circle, then I have covered half of my circumference, then I am looking at half of my area. So exact same logic here, except now our new whole isn't going to be 2 pi r, it's going to be the area of our circle, which is what? Pi r squared. So the area of our sector is going to be either, again, this theta in terms of degrees over 360 degrees, or theta in terms of radians over 2 pi, and I am multiplying that by our pi r squared, our new whole. But again, the logic here, exactly the same. Fraction of the circle times whatever units I'm actually converting. Questions with our definitions for arc length and sector area? Hopefully the exact same thing that we just did, but now we're changing it to be either a piece of our circumference or a piece of our area rather than a piece of our degree measure or a piece of our total radian measure. But exact same logic. Totally pervasive throughout this whole thing.
The arc length is S and the sector area is A.
That's just how they're commonly denoted. I actually don't know if people normally refer to sector area with this. I've seen, I think in the notes that I was using off of this, they did like big capital S. I know arc length is often denoted by little s because, you know, of all the s's that are in the word arc length. And sector being capital S makes a little bit more sense. But I like to denote it with this A sub S just to kind of indicate it's an area. In particular, it's the area of the sector. But you can denote it however you like. This is by no means the only way that you'll see it, and it is certainly not the only way to do it, just so that you're clear that that is what this is referring to. All right, let's take a look at example 3 here. I'm going to take a stab at 3B, and then I'm going to give you guys a fair bit of time to work through A and C. For 3B, we are told we are looking for both the sector area and the arc length. And in this case, we are told that our theta is equal to 100 degrees and that our radius is equal to 14 feet. Okay. So what do I need to find for, or maybe not need to, but what is my recommendation for what we do first? Yeah, figure out what fraction of our circle this 100 degrees represents. Take 100 degrees and divide it by 360 degrees. Again, this is just telling us what part of our circle are we looking at. How much of our circle have we rotated around? Works itself out to be between like 30 and 33 degrees, but we actually can simplify this pretty easily. 10 over 36, 5 over 18. So 5/18 of the way around our circle, a little less than a third. Okay, so this is our fraction of our circle. How do I use this then to find my arc length? Let's start there. Multiply by the circumference, in this case, multiply by 2 times pi times, we said our circumference is 14. And then if I wanted to find my sector area, rather than multiplying by my full circumference, what would I multiply by instead? Pi r squared, my full area, pi times 14 squared, which is my, again, full area. And you can plug this into your calculator, and so this works itself out, I think, to be like 70 pi over 9. And this one, I think one person in another class simplified it, and I don't want to, so I'm just going to circle this. In particular, this is my, again, piece of an arc length. This is arc length, and this is sector area. First finding, how much of our circle have we gone around, what fraction of our circle, what percentage of our circle, and then multiplying it by whatever that means to us. If I've gone 1/4 of the way around a circle, then I want 1/4 of the area. If I've gone 2/3 of my way around the circle, then I want 2/3 of the circumference, whatever that value is. All right, take a stab. We're going to take 10 to 15 minutes on this. C is a little bit tricky. We'll take a little bit longer. Take a stab at A and C. In particular for C, try and really digest what information have you been given, and then can we use the same idea, same methodology? 400 times 400 times. Okay.
I can just multiply by 14.
Sure, you can do that. Yeah, that'll work. 70. 14 times 5 is 70. Yes. So we're doing A and C. Yeah. So this is a good start. So how much of our circle is that? Did that one on the previous page. Well, what fraction of our circle is that? 124. And in this case, we're looking for arc length. So that's a piece of our, yeah, it's gonna be the circumference. Exactly. Okay, this is good. If you want to simplify it with your calculator, enter in the same thing and then just leave off the pi, but then include the pi in the numerator of whatever your answers. That should work. But also, you don't need to simplify. Perfect. Yeah. Sure. We want to be extra clever with this. So what is the 150,000? What is that? Everything like a sprinkler system, right? It's gonna be, yeah, exactly. So it's a piece of our area. So that's like the sector area there. Okay. So you could set up that equation and solve it. Totally. But you could also think about still kind of using this logic of like, okay, if I have 150,000 as my piece of my area, as part of my area, what fraction of my total area is that? And then use that to convert to a theta as well. And that'll work as well. And both ways are totally fine. Yep, looks good. So just 150,000. Okay, so if we're thinking about, so think of like this irrigation system. It's like just a giant sprinkler system, basically. So it's possible that I could get one, but for that to happen, the water would like just need to be going to the circumference and like not touch any of the area inside, in which case it's probably a pretty bad sprinkler system. So what is the probably, what is the 150,000 probably referring to the area? A verbal clue would be like the fact that it's a square meters, kind of makes this neat area, but also just think like giant sprinkler system, just spraying like a little triangle. So you could set this up and solve the data. You can also think, what fraction does that 150,000 represent?
What's the alignment? This is some kind of great like sigma.
This is the theta.
What?
Theta.
Theta?
Yeah, it's just what we use for angles for the most part.
So
It's like x. Think of it like x.
that would be, if we use the chain, that would be about radius of 6 meters, that would be 6 meters.
So it would be, so the theta that we're going to use is basically just the degree. It's the angle.
That's 6.
So r would be the 6. 15 is the degrees. That would be the thing.
Because.
Yeah.
I thought it was.
Pi times, okay, so theta times. Okay, now is it just theta? Is it theta alone?
Theta.
Theta You can either do theta, you can do theta sub r, that would work. But it's always that proportion. It's always either theta over 2 pi if you're doing radians, or theta over 360 degrees. Either way, it's fine.
So it's gonna be theta over 360.
Yeah, you can do 360 or 2 pi. Yeah, it doesn't specify.
Am I supposed to do 2 pi? Am I supposed to have it like 5 times 4?
Pi r squared, sorry. Because thinking like if we've got this giant sprinkler system, it should be, we would hope that all the water isn't going just to the edge. We would hope that it's like spraying the entire thing.
And then I just solve it like an awesome problem.
Yeah, you should totally good. Yeah. Okay, that's perfect. And then what is this go? Pi r squared we're looking at here. The 2 is only for the. Yep. And so then what is the, what is this going to be equal to? What is this sector area? So this is what we're looking for. The setup looks perfect. What is this going to be? What is that cone? What other piece of information I got? We're getting the radius, but you incorporate that. This looks good. This side of your equation looks great. What is this 150,000 going to represent? Yeah, it's there. That is the sector. So this should be offset, should be equal to that 150,000. We need that cone area to be 150,000. Otherwise, we're at the cone. Yeah. Thank you.
So I can solve 337.5 over.
Yep. That works. And that would be in degrees?
Yeah.
So you might want to just get all degrees on it. So this is pi r squared, right? So this is our total possible area. What do we know about our sector area? Yeah, that's gonna be that 150,000. And so you could like plug in for pi r squared, you could plug in for the sector, solve for theta. That would certainly work. Okay, I am going to, let's go over this right here. For A is not too different than what we looked at with B. In fact, just less, just finding the arc length. So looking at 3A. For 3A, what are we told about our value of R? What about our value of theta? R is 6, theta is? Well, that'll be the fraction, and the theta that corresponds to that fraction is 15 degrees. But Haddon is absolutely correct. What does this theta represent? This tells us that we have gone 1/24th of the way around the circle, which is good. So taking that 15, dividing by 360, and then what am I doing with this 1/24? I want to find 1/24th of what measure for arc length? 2 pi r of the circumference. So 1/24th times 2 pi times r. 12 pi over 24. This becomes pi over 2. Or you could leave it as 1/24 times blah, 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 blah. That's fine too. Pi over 2, just a nice kind of simplification for it. Does this correspond to a 90-degree rotation with this circle setup that we have? It's tempting to say yes, because, oh, wait, pi over 2. We know pi over 2. Pi over 2 is up here. That's 90 degrees. So 15 degrees is equal to 90 degrees. Except that statement doesn't make any sense. And so why then do we see this pi over 2? Well, the way that I kind of like to capture it or display it is if we're thinking about increasing our distance, we've got some kind of rotation here that is giving us an arc length, some kind of distance. We could travel farther by traveling farther, right? We could rotate more. And that would certainly travel us farther. But we could also travel farther if we swing out wider. We could rotate the same amount, but travel farther by increasing the radius. In particular, pi over 2 only is analogous to a 90-degree rotation if the radius is 1. In this case, because the radius is 6, that pi over 2 distance means absolutely nothing in terms of 90 degrees or whatever. It is just 6 times whatever that normal 15-degree rotation would take us. All right, so the pi over 2 that we see here is not the same as the pi over 2 that we see up here. This pi over 2 comes explicitly from a circle with a radius of 1. This one is a small rotation in terms of the theta, but a much larger rotation in terms of a door. Think if I swing a door open, having a longer door means it will have to travel farther. The edge will have to travel farther in order to make that swing happen. Okay, so we get pi over 2, which is not 90 degrees. This is, in fact, meters. This is just a distance that we have traveled along a circle. And it's a big enough circle that we travel that distance with just a tiny little 15-degree rotation. All right.
How did you get that, though?
1 over 24, so this is the fraction of our circle, times the circumference of our circle, which in this case was 12 pi, or 2 pi times 6.
What about the version of, I forgot what it's called, the bottom one?
This one here?
Yeah.
We weren't given the theta in terms of radians. If we were given the theta in terms of radians, we would use this one instead, but we weren't, so we used the degree one. You certainly could convert to radians first, but why add an extra step when we don't need to? It's the same formula. One is just for when we're given in degrees and the other is for radians. Or do you mean the sector area formula?
Oh, no, it's just.
Yeah, it's because it's 15 degrees rather than like some kind of radian.
Theta?
Yeah, the degree is the theta. All right. Now for C, C is a little bit tricky. We're given weird information for C, not that kind of standard what we would normally expect for C, but certainly stuff that we can parse through. What is the information that we're given? What are we told? So we're told the area of a sector, a piece of the area. In particular, we're told that the sector area is equal to 150,000. Think if we have a sprinkler system, I can only water a fraction of my total area. That amount that I can water is 150,000, however many feet, square feet. And then what else are we told? Radius is 400. Now you absolutely could, I think most people did, use the sector area formula, plug in what we know, solve for theta. Totally works. That's great. But I want to try and do this in a very consistent way to what we have done up until that. Nothing wrong with that. It requires you to know a formula, and I like not having to know formulas. It's just my personal, jam. Is I like not having to know formulas. So how could we approach this in a similar way to what we have been doing overall? What do I need to find first? That we've always been finding first. The fraction of our circle. Now, before we were given angle measures and used those to find the fraction of our circle. What are we given here, though, that we're going to use to find the fraction of our circle? We're given a piece of our area. And can we find the total area that we would normally be looking at? Absolutely, we can. So in particular, our fraction is going to be this 150,000 over the total area of my field, in this case, 160,000 times pi. So again, this is my fraction. Fraction of a full circle. How far away am I from covering the full area? I've got it's about 30%. Plug it into a calculator.
How'd you get 160,000?
That's pi r squared. Where r is 400. So 400 squared is 160,000 times pi. Now notice this is slightly different than the formula that we're looking at up there. It's like a rearrangement, we'll see, of that formula. But either way, the logic, prevailing logic, we have found the fraction of our circle. It's about 30% of our circle. How can I convert that to an angle measure? Multiply by 360, that'll give me an angle measure in degrees. What else could I do? Are degrees the only angle that we have to work with? No, what else could I do? Multiply by 2 pi, that would give me radians. Either way is totally fine. 2 pi actually works out to, the numbers work out pretty nice. You get like 15 over 16 pi. If you multiply this by 2 pi, you get 15 over 8 radians. Or if you multiply this by 360, you can get what, like 107 point something? 43, sure. And that would be in degrees. And either way, it's fine. Is there anything wrong with taking the formula, plugging in a sub s, plugging in whatever, plugging in r, solving theta? No, there's nothing wrong with that. That's totally fine. But I really want you to feel the logic that we see here. Right? We're looking at what fraction of our whole do we have. And then we're essentially pushing that through and saying, okay, well, that means that if I cover 30% of my total area, then I have to rotate by 30% of the total possible number of degrees. If I cover 30% of my area, then the circumference that it traces out would have to be 30% of the total possible circumference. You can really take this idea and run with it, the idea of figuring out what fraction of our circle have we rotated around, and then run from there. All right, questions with what we see here?